How far will it go? And how high will it fly? Every airplane has its own unique performance capabilities and limitations. While one can fly extremely fast, another can take off and land on very short runways. It's not only important that you realize different airplanes have distinctive capabilities, it's also essential that you understand that an airplane's performance varies considerably under different flight conditions. Altitude is a primary item affecting performance. Specifically, as you gain altitude, the atmospheric pressure decreases. With a normally aspirated engine, the less dense air reduces engine power and overall airplane performance. It's essential that you consider this when operating at high elevation airports. Air density also decreases as the temperature rises because air molecules expand as they are heated. Therefore, the performance of your airplane diminishes on hot days. Finally, if the humidity is high, the air entering the engine contains water vapor, which takes up space normally available for vaporized fuel. This moist air tends to retard even burning in the cylinders. One of the most effective ways to determine how your airplane will perform is by computing density altitude. Earlier, you learned that density altitude is pressure altitude corrected for non-standard temperatures, and that they equal one another only when standard conditions exist. Now let's look at an example of how density altitude is calculated and what this value actually means. Imagine that you will be departing an airport located at sea level. If standard atmospheric conditions exist, your airplane should perform as expected for sea level operations. Let's assume that the pressure altitude is the field elevation. However, the temperature is 40 degrees Celsius, or 25 degrees above standard. By using a chart or flight computer, you'll find that at 40 degrees Celsius, the density altitude is approximately 2,800 feet. This computed density altitude value means your airplane will perform as if it were departing an airport nearly 3,000 feet higher than the one where it's actually located. Because the density of the air is so much less with this above standard temperature, your airplane's performance will diminish. It's important to remember that the higher the density altitude, the lower the airplane performance. Remember that high altitudes, high temperatures, and high humidity all equal a high density altitude. Most modern performance charts have the density altitude computations built into them. But before we look at some of these performance charts, let's consider a few other factors which influence performance. You have learned that the air moving around the wings produces lift. Likewise, existing wind conditions have a big impact on airplane operations, specifically takeoff and landing performance. For example, headwinds are desirable for both takeoffs and landings. During the takeoff roll, a headwind supplies additional lift to the wings. This enables you to lift off earlier than during a no-wind condition. During a landing, the headwind reduces your ground speed as you approach the runway. This, in turn, shortens the landing roll. Aircraft performance can also be influenced by the runway itself. Many runways slope from one end to the other. You need to consider the gradient when determining takeoff and landing distances. For example, if you land uphill, the airplane will decelerate faster than normal, which will decrease the landing roll distance. On the other hand, departing uphill will lengthen the takeoff roll since it takes longer to accelerate to liftoff speed. The opposite conditions exist when the runway slopes down. Now your takeoff roll will decrease because you're able to accelerate faster. However, your landing roll will increase because it takes longer to slow down. You should also pay close attention to the effects of operating on runways with surfaces of snow, mud, water, or grass. The friction produced by these surfaces may significantly increase your takeoff roll. Now let's turn our attention to some examples of performance charts that you'll likely encounter during your flight planning. The most important source of information available for these calculations is the pilot's operating handbook. However, the performance data from each POH applies only to a specific aircraft. Therefore, when you're determining the performance figures for a particular aircraft, make sure you're using the correct POH. Suppose you're going to be departing a short field and you want to know the ground roll and total distance required to clear a 50-foot obstacle. For this type of calculation, you'll need to refer to the takeoff distance chart. Before beginning, you need to note the conditions necessary to achieve the computed values on the chart. These include the flap setting, the power setting prior to brake release, the runway conditions, and the associated winds. Other notes are included for making adjustments for varying wind and runway conditions. For this example, let's assume the following conditions exist. The pressure altitude is 3,000 feet. The temperature is 20 degrees Celsius. And the airplane is at its maximum takeoff weight of 2,400 pounds. The table lists the appropriate airspeeds for liftoff as well as the recommended speed once you're 50 feet off the ground. These airspeeds help to assure that the airplane will perform as shown. First, locate the pressure altitude of 3,000 feet. And then move horizontally to the current temperature of 20 degrees Celsius. Under these conditions, the ground roll distance is 1,230 feet, and the distance required to clear a 50-foot obstacle is 2,295 feet. As you can see, this chart does not cover every temperature or pressure altitude possible. Therefore, it's often necessary to interpolate values between the given variables. Now let's examine a cruise performance chart for a Beechcraft Sierra. This type of chart is extremely useful for estimating the speed of your airplane as well as the fuel consumption at various altitudes and power settings during cruising flight. For this problem, let's assume the following conditions exist. The propeller will be set to 2,400 RPMs. The airplane weighs 2,600 pounds. The pressure altitude is 2,000 feet, and the temperature is standard at this altitude. After verifying that you have the correct chart, start with the pressure altitude of 2,000 feet. Move horizontally until you reach the information for a standard day. Within this area, you'll find the manifold pressure you should use to achieve the desired results. In this case, it is 22.3 inches. The fuel flow at this power setting is 54 pounds, or 9 gallons per hour. And the true airspeed is 120 knots, or 138 miles per hour. Landing distance charts are also helpful planning tools. Although they vary somewhat, they're designed to enable you to determine how much runway is required to land the airplane safely. This is particularly important if your destination airport has a relatively short runway. The layout used in this particular chart provides precise landing information as long as you follow the specified conditions. For example, this chart is only valid during a power-off landing with the flaps set at 40 degrees. While some landing charts provide just the ground roll distance, this one is designed to show the total distance required to land over a 50-foot obstacle. For this sample problem, we'll assume the following conditions exist. The temperature is 30 degrees Celsius. The pressure altitude at the airport is 4,000 feet. The airplane's landing weight is 2,100 pounds. And you're landing into a 5-knot headwind. Now use these values to predict the landing distance by following a path through the graph. The first step is to locate the current temperature of 30 degrees. Next, proceed vertically to the 4,000-foot pressure altitude of the destination airport. Move horizontally to the weight reference line. And then move diagonally to the airplane's landing weight, which is 2,100 pounds. Continue horizontally to the no-wind reference line. Then move diagonally until you reach the current headwind of 5 knots. Now move straight across to read that the landing distance over a 50-foot barrier is approximately 1,080 feet. Because your airplane's performance can vary substantially, it's vital that you understand how changing conditions can alter its usefulness. As you gain knowledge of how density, altitude, surface winds, aircraft weight, and runway conditions affect the airplane, and learn to use performance charts properly, you can safely and accurately predict the capabilities as well as the limitations of your airplane.